Let's begin by opening up the msAxel program, clicking on its icon here, as you can see where the cursor is, and this will start up the msAxel program. If you're using the DART, the DART will be started up independently through its browser link. Now, the program's starting up, and we'll see the startup window in just a moment. We're in electrospray mode, and I'd like to start in DART mode for this example. So we're going to change the ionization mode here. Now, in order to do that, the instrument has to be in either evacuation ready mode, as if it had just been pumped down, or if it had been set into standby condition, or waiting mode. You can't change ionization modes if you're in operate. So let's click on DART+, and then the program is going to prompt us to open an MS method, which is a set of saved tune parameters, voltages and temperatures and things like that. So we'll click on this and we'll choose the DART+ tune method. The program will go ahead and load those methods, and then you'll see on the left the tune monitor. This is an emulator, of course, so this is just going to be digital data. But on the right, you have a zoomed-in region. So let's just look at these. If you drag the cursor from left to right, you can zoom in on a particular region. If you double-click, you can get back out. And if you draw a box with the cursor, you can zoom in both vertically and horizontally. If you're zoomed in, you can use the left mouse button to move either the X or Y axis up and down. And we can double-click to get back out again. Typically, we'll look at the full spectrum on the left and the zoomed-in region on the right. And keep in mind that these are just for tuning. None of these things that you see in these windows are saved unless we're actually acquiring a data file. On the left, you have the MS status monitor, and if you click on that, this will show the instrument conditions. Clearly, we're operating with an emulator right now, so it thinks that Orifice 1 is not very hot, and you can see there's an error condition there. If you run into problems, the service engineer will ask you to click on the MS status button and take a look at the information here, which shows the requested and actual voltages and temperatures and other parameters for the instrument. Let's go ahead and close that if we can. How do we do that? I think we just toggle it by clicking that button. And then below that, you'll see the vacuum condition for the atmospheric pressure interface and for the analyzer, as well as a disk space monitor. At the top, you can see the current calibration, which is the default calibration for this instrument condition. There are separate calibrations for positive and negative ion mode, and also separate calibrations depending on what the largest measured mass is for your acquisition conditions. If we click on the ellipsis, you can see the current calibrations. Now, if you have a maximum mass of maximum m/z of 1,000 or less, it will use this calibration for positive ion mode. If your maximum measured mass, the maximum mass that you specified for your data acquisition is m/z 2,000 or less, we'll use this calibration, and so on. And you can click on the ellipsis to choose a calibration. Now, by default, it's going to try to find a calibration that matches your conditions, but you might choose to use a calibration for a different mass range. So let's just look at positive ion calibrations, and you can see any of these calibrations would be suitable. So we'll just go ahead and change that one, or change it back to use some calibration file that is measured on your system in positive ion mode. And then there'll be a corresponding set of negative ion conditions. It's okay to use a calibration to a lower mass range to extrapolate to a higher mass range, as long as you're not trying to do exact mass measurements. So here we're using the same calibration even up to m/z 2,000, although it was probably only measured to m/z 1,000. We'll go ahead and close this. Then, because we're in waiting mode, we wouldn't actually see any signal, but let's go ahead and switch to operate mode. And if this was a real machine, you'd see the noise in the windows change to show you peaks, and that's assuming, of course, that the DART is operating. There would also be some current measured on Orifice 1 if this was actually a real system. Now, the Tune tab shows you the most important parameters for operation. Because of the simulator, it's not going to read the orifice temperature, but I'm going to leave it like this just for a minute to show you what happens if the temperatures are not reaching their set point. Typically, I'll run the DART temperature, the Orifice 1 temperature at 120 degrees. That keeps the orifice clean, and it also causes the metal to expand a little bit and shrink the diameter of the orifice so that it isn't pumping quite as much helium and doesn't stress the vacuum system too much. The detector voltage is going to be different on each person's system, so you'll have to determine that yourself. You want to choose a detector voltage probably somewhere between 1900 volts and 2400 volts that gives you a strong signal but doesn't cause your peaks for your most abundant compounds to be off scale to saturate the detector. If the peaks are off scale, then both the X and Y values will be wrong. The mass accuracy won't be very good, and the isotope ratios won't be very good. But just set this appropriately so that you have good signal to noise. Remember that if you increase the detector voltage, of course you're going to increase signal, but you're also increasing noise. So it's okay to use a conservative value as long as your signal to noise looks good. The values on the right here are for the atmospheric pressure interface. The Orifice 1 voltage, for example, is showing you the potential difference between Orifice 1 and Orifice 2. That's the field that the ions experience as they enter the atmospheric pressure region. And 20 volts is a very gentle potential. So for DART, we typically use a 20-volt Orifice 1 setting for spectra that don't have very much fragmentation. The ring length potential defines the potential difference between ring lines in Orifice 2, and the Orifice 2 potential defines the potential difference between Orifice 2 and the RF ion guide. There are other settings under advanced settings, and these are used when you tune the instrument, but you should never change these unless the instrument needs to be tuned again. So we're going to turn those off, and we won't even discuss that for now. Generally, the new AccuTOF systems rarely ever need tuning once they've been set up initially. The RF ion guide voltage is going to define the lowest m/z that you can measure. So as a rough rule of thumb, take this value and divide by 10, and you can see then our lowest m/z is going to be approximately m/z 50. Above that, all of the ions are going to be passed. It's not a step function, it's a S-curve, so if you really need to measure m/z 50 with good sensitivity, you may have to set this to a lower value. I'm going to say that we just want to measure m/z 60 and higher, so I'll leave this at 500, and if this was a real mass spectrometer, not a simulator, you'd see peaks down around 50 and higher, and then above some value, the response is essentially flat. These values can be changed on the fly if we do parameter switching, and we'll discuss that a little bit later. But these are typical settings for DART. The values for these will change for electrospray, and that's going to be a separate discussion, but electrospray requires really that you tune on some kind of model compound because the optimal values for these will change depending on the size of the molecule and so on. The Data Acquisition tab specifies the measurement conditions. For example, the mass range that will be stored to disk is shown here, low mass to high mass. The lower m/z should reflect the lowest m/z that you specified the RF ion guide to pass. It wouldn't make much sense to set this at 2500, which is the maximum value, and pass m/z 250 and higher, and then tell it to save data from mass 50 and higher. So let's make sure that the RF ion guide value matches your for data acquisition. The time range specifies the time at which the data acquisition will shut down automatically. You can always stop the acquisition by pressing the stop button before that time, but when data acquisition reaches 15 minutes, it's going to stop. If you want to change that, you can change the value. Let's say we wanted to run something for 20 minutes. We'll just go ahead and enter that value there. The values over here specify how fast data are saved to disk and how many milliseconds per data point are going to be acquired For most low mass measurements up to about MRZ 2000, you want to use 0.25 nanoseconds per data point. This is a 4 gigahertz digitizer, and this is the smallest time interval per data point you can use. That's going to give you the largest number of points per peak in the mass spectrum, which is going to give you the best mass accuracy. If you were to acquire to very high MRZ, say MRZ 8000 or 10,000, the software may require that you use a slower sampling interval. But for now, let's stick with 0.25 nanoseconds per point. The recording interval is the spectral storage rate. This means that you're going to save one spectrum to disk every 1 second. The maximum rate is 50 hertz, so your fastest speed would be 0.02 seconds per spectrum. Of course, this is going to give you a larger data file, but for DART, let's stick with the slowest value, which is 1 spectrum per second. Most DART measurements are relatively slow, and so that's a perfectly good value. Now, if you acquire at a rate of 1 spectrum per second, the time it takes to write the data to disk is 3 milliseconds, so that you're actually acquiring data for 0.997 seconds, and then there's a 3 millisecond wait time between spectra. This is the fastest wait time you can use for typical measurements, but if we are doing voltage switching later, then we'll use a 30 millisecond value, and I'll explain about that in a minute. The real-time display is going to show you the runtime mass spectrum and the total ion current chromatogram, but you can also specify that you'd like to monitor specific masses at particular times. So if we click on the extracted ion current chromatogram button, then we could say we'd like to measure, let's say we're going to measure cocaine with DART, then you want to bracket the mass that's observed. Protonated cocaine is at 304.15488. If we don't know the exact value, let's just say 304 to 304.3. You can have up to 4 measured masses in runtime, and bear in mind that this is just real-time feedback. It has nothing to do with the measured spectrum. You can create mass chromatograms for the data afterward and during data processing, but if you just like to have some real-time feedback on the behavior of a particular mass versus time, this is the way to do that. Actually, let me stop here for a minute. Where we really should have started with all this is to create a project. So let's just stop for a minute and do that. The project contains data, but it also contains tune parameters and other files that might be customized. So before we do anything, let's create a project with these parameters and with everything else, and we'll work within that project. You can have projects for different operators or for different research projects, whatever you like, but use the projects to organize the data and the tune conditions. So under File, New Project, the software is telling us that we have to be in wait mode before we create a new project. So let's do that. And then let's create a new project, and we'll just copy the parameters from this project into a new one. So it's asking us if we want to save the changes to the method. Let's say yes. Let's save those as training video DART plus. This will save the voltages and temperatures and everything else that we specified. And we'll save that in some folder. You can change the name of the folder at any time. When we make the new project, it's going to have this name, and it's going to copy these parameters that we've saved in a previous project. It's not going to copy the data because we haven't checked this box, and typically you don't want to make a duplicate of your data. You just want to copy the measurement parameters like this. Okay, now here's our new project. The name will be displayed at the top of the window. We'll go back to operate mode. And now all the new data that we measure will be saved in that project, and it's in a folder under that project. You cannot acquire data and save a measurement to a file unless you've previously saved the method. So if you haven't saved the method, make sure you save the MS method here. And then the single run button will be activated. If you haven't saved a method, then this will be grayed out and won't be active until you've saved your tune conditions and everything else. Let's hit the button, and it's complaining that it couldn't start something. Well, let's see why that is. Under details, it tells you because Orifice 1 temperature hasn't reached the setting temperature yet. Well, that makes sense because there's no real hardware attached to this. Let's cheat that by telling it that we really want 0 degrees, or even just turn off the Orifice 1 temperature because it doesn't exist. But in reality, you're going to want to set that to 80 or 120 degrees. The program will not allow you to acquire data until the set point is within 20 degrees of the actual temperature. So we'll save that again because you saw that the single run button was grayed out. And now I'll hit the button, and now it'll let us save data. So let's just say DART plus example for video. And we can save that in some folder and specify information here, any information you'd like. Okay, so that will be saved in the data. There are things we can do automatically. We can do automatic block mass correction for exact mass. We can automatically have the data exported in that CDF file, but let's not do that right now. We'll just go ahead and save profile data, which means we're saving all of the peak shapes and all of the data points for every peak in every mass spectrum. Centrated data is bar graph data or histogram data. That will be a smaller data file. But let's stick with profile data for now because that will let us inspect peak shapes and check the signal to noise and things like that. So you hit the Run button. The program will get ready for measurement. It's going to go to the monitor window. And then it's going to wait for the start signal. Now, the start signal can come from an auto sampler or for contact closure. But if we're going to start a manual measurement, then we can initiate that by hitting the Go button. As soon as we do that, we'll see the real-time monitor windows. So let's hit Go. And now if this was a real mass spectrometer and not just a simulator, you would see the total ion current chromatogram changing here as the background and signal change. If you measure the signal, you'll see the chromatogram increase. And you'll see the mass spectra change in real time. I notice that this is not showing me the extracted ion current profile that we requested. And that's probably just because this is a simulator. But in reality, you would have 3 windows. You'd have 2 chromatograms, one for the total ion current and one for the extracted ion chromatogram that we requested, and then also the real-time mass spectrum. You can grab the splitter bars in any of these windows and reapportion the way the windows are set up. At runtime, you can see the current time and the end time for the spectrum. And if we'd like to go ahead and stop, then we can just hit the red stop button and halt data acquisition. And now we're done. At this point, you could go to the data processing window and process the data as I discussed in a separate video. Now, if you have an auto sampler, you can set up a sequence of files here to be run. And these buttons will start and pause and stop the samples in the autosampler sequence. That's subject for a different discussion, but I just wanted to explain what these extra windows are. If we have process data, then everything we've measured is going to be recorded in the data acquisition history down here. And you can see we've already acquired one virtual mass spectrum here. Let's go back to the MS window, and let's look at function switching. Under Tools, Parameter Switching, you can specify that you'd like to change the voltages, for example, on the Orifice 1 potentials here. If we turn this on, you can see the default is we've got 20, 30, 60, and 90 volts. As we increase the Orifice 1 potential, the ions are going to experience a higher acceleration as they enter the atmospheric pressure region, and then typically you'd see little or no fragmentation at 20 volts, maybe a little bit of fragmentation with 30 volts, but at 60 and 90 volts you'll see a lot more ion fragmentation. So we could have the function switching automatically on the fly so that for one measurement we've measured a spectrum with little or no fragmentation and 3 other spectra with varying degrees of fragmentation. The ring lens voltage is typically 5 volts, but you'll see during a training class or later that at 90 volts, it's probably better to increase the ring lens voltage a little bit to prove this 90 volt spectrum. So we'll go ahead and set that to 10 volts, and leave the others the rest of the way. You could also change the fine guide voltage on the fly to change the lower M over Z that's being required. But for now, we're going to leave all those the same. And we're going to specify 0.2 seconds per spectrum. So the software is going to cycle through these voltages. Every 0.2 seconds, it's going to switch 20, 30, 60, 90, 20, 30, 60, 90, and so on throughout the spectrum. So that as you've acquired the measurement for your sample, you'll wind up with 4 parallel data files, one for each different collision energy. The maximum speed that you can acquire data if you're changing voltages is 10 hertz. It won't do the 50 hertz that you can do if you're just running a constant voltage. And notice the wait time between spectra has been changed from 3 milliseconds to 30 milliseconds, because this is the minimum time it takes for the voltages to settle between requests for different voltages. Let's go back to 5 spectra per second, which is a pretty typical value, and just say OK. Now, if we were to measure data here, notice it says parameter switching is on. And don't forget, you have to save the tune condition. So let's save this method as DART plus switch Orifice 1. And then having saved that method, then the single run button is now activated. I'm not going to acquire data with that because we're using an emulator, but we can do that during a training class. Let's turn the parameter switching off again, and now you can see that message is no longer displayed. We'll do one more thing. We'll pretend to switch to electrospray mode. So we'll go from here to waiting, because you can't change ionization sources unless you're out of operate mode. And we'll switch to electrospray plus. Again, it's asking if we want to save the changes to the parameter set. I'm just going to say no. And let's open a method for electrospray. Now, if you're switching from positive to negative mode, it's going to take probably about 20 seconds to switch over. But from positive to positive, it's a pretty quick switch over. You'll see several new parameters here on the tune page. The first is the electrospray needle voltage, which is typically 2,000 to 3,000 volts. If you were using APCI, that could go up to 5,000 volts. There will be a desolvating chamber temperature, which is also a new parameter. That's the heater chamber in the electrospray source. And that typically goes to 200 to 250 degrees C. That's going to help to nebulize the solvent. The nebulizing and drying gas checkboxes are checked here, and these will turn on the valves for those two gases. The actual flow rates are set with the dials on the instrument itself with little bubble meters. But these things will both turn on the nebulizing and drying gas flow. And the rest of these are the same, but notice the Orifice 1 and ring lens and Orifice 2 voltages are different here. Those values are going to change depending on what kind of molecule you're measuring with electrospray. So for example, if you're measuring proteins, you're probably going to have to set a higher voltage, maybe 120 volts or so. The best way to determine that, of course, is by looking at some sort of standard tuning compound that's similar to the things you want to measure. If you're not sure electrospray mode, you can always use function switching to try to find an optimum value. Other than that, the acquisition settings are no different than they were with DART, and the ion guide voltage is set appropriately. But that's pretty much it for data acquisition in msAxel. One more thing, there is a reference editor up here, and that can be used to set up a calibration compound. We'll discuss that separately. Anything else? No, I think that's a pretty good place to stop. So we'll go ahead and close out the video here.